Lesson 2.4 is the library of functions and piecewise functions. Parent functions are the base function before any transformation has been applied. The 6 parent functions we're going to start looking at are linear functions, quadratic functions, cubic functions, square root functions, reciprocal functions, and absolute value functions. And we're going to get a little bit more detail about how exactly we graph these and what the parent points are, but we need to have these parent functions memorized so later on we can apply transformations and be able to graph these graphs. Another parent function that we talk about a little bit is the greatest integer function, which whatever the input is, the output will be the greatest integer less than or equal to that input. We notate it with this like double bar bracket or INTX. This is kind of the graphing calculator notation for it. And whatever your input is, it will give you the integer that is less than or equal to whatever your input is. So for example, if you input an integer, your output is going to be that exact same integer, whether it's positive, negative, or 0. However, if you input a number that is not an integer, the output will be the largest integer that's already been achieved. So for example, for f of 0.5, or the greatest integer of 0.5, then the greatest integer that's been achieved is 0. So at 0.5, the output is 0. At 1.7, the greatest integer that's been achieved is 1. So at 1.7, it's 1. So anything between 0 and all the way up to 1, but not including 1, is going to have an output of 0. Everything from 1 up to but not including 2 is going to have an output of 2. Everything from 2 up to not including 3, so on and so forth. So it looks like this. Where it gets a little bit tricky is the negatives. So for example, if I have f of negative 2.5, so the greatest integer of negative 2.5, the greatest integer that's been achieved so far is actually negative 3, because negative 2 hasn't been achieved yet. So for the negative steps, it's kind of underneath what you would think, or the one below what you would think. So it looks like this. It's also sometimes called a step function because it literally looks like a set of steps. A piecewise function is a function that uses different equations on different parts of the domain. So for example, f of x equals negative x plus 1 if negative 1 is less than or equal to x is less than 1. So it looks like this graph, but only on this section of x's. And then f of x equals 2, but only when x equals 1. And f of x equals x squared, but only when x is greater than 1. So on different parts of the domain, the function is going to behave differently. So for example, if we want to find specific outputs, if I want to find f of 0, I'm going to find the section where x equals 0 lives and only apply that part of the function. So for example, x equals 0 lives in this first section of the domain. Negative 1 is less than or equal to x is less than 1. So I'm going to plug in x equals 0 only into that first part of the function, negative x plus 1. So I get negative times 0 plus 1, and so I end up f of 0 is equal to 1. For f of 1, I want to find where x equals 1, which is in the section where it says if x equals 1, y equals 2. So my output is going to be 2. And then for the last one, for f of 2, I'm going to find where x is greater than 1, so 2 lives there, plug it into x squared, 2 squared is equal to 4. So I look at what section of the domain that x coordinate lives in, and then I plug it into that part of the function. For number 2, it says find the domain of f. So I'm just going to look at the domains individually that they have here and then just try and combine them together as much as possible. So the smallest x value that is allowed in any of these domains is negative 1. And then I go all the way up to not quite 1. And the next one I jump down and I do include 1. And then the next one I want everything bigger than 1. So I want to start at negative 1 and I want to go all the way greater than 1. So my domain is all x's that are greater than or equal to negative 1. So you just kind of look at those individual domains and see if you can combine them together as much as possible. For the range, I'm actually going to skip that one and I'm going to graph it first. A lot of times it's easier to see the range of f on a piecewise function after you've graphed it. So when we graph it, we're going to graph each section just like the function that it says, but only in the domain that it says. So I'm going to graph the line negative x plus 1, but only between negative 1 and 1. I plugged in negative 1 into the function in this part just to see what my endpoint would be. So negative 1 comma 2, and then I know I have a slope of negative 1, and I'm going to go all the way until x equals 1. I want to include x equals -1 in that part of the function, so I'm going to have a closed circle here. But at x equals +1, I don't want to include it in this part of the function. I want everything up to but not including that. So therefore, I'm going to put an open circle that denotes that it doesn't actually exist at x equals 1. For the second part, it says that if x equals 1, then y equals 2. And that's just a singular point because it's just one specific x value. So at x equals 1, y equals 2, and I drew a coordinate point, and that's that second part. So then for the last part, I'm going to do the same thing. I'm graphing x squared, but only for x is greater than 1. So I did the same thing where I plugged in 1, even though it doesn't actually exist at 1, just so I had an endpoint. But because I don't want it to actually exist, it's not or equal to, I put an open circle there. So I want to start there, but not actually include it. And then it looks like the parabola x squared from there. So now I have the graph of this piecewise function. A couple things to check is to make sure that you don't have anything overlapping. So for example, if these were closed circles, this would no longer be a function. Piecewise functions are functions, which means you need to make sure it passes the vertical line test. So now I can use this graph to help me find the range of this function. So I noticed that the lowest y value I achieve is not quite 0. I have an open circle here, so I don't want to include 0, but everything greater than 0 all the way up, and then if I jump over, it goes on forever, up towards positive infinity. So my range is going to be all of my y's strictly greater than 0. And so now I have the range of that function as well. One parent function we're going to get a little bit more in depth about is the absolute value of x. So the absolute value of x can actually be written as a piecewise function because there's different things happening in different places. So go ahead and pause the video and see if you can write the absolute value of x as a piecewise function and then graph it. For the absolute value of x, the breakpoint is 0 because you're looking at different things that are happening in the positive x's and the negative x's. So for x's that are greater than or equal to 0, whatever your input is for an absolute value, you get the same value back out for its output. So therefore, its output is just x. So for your positive x's, nothing changes. So that's why this side of the absolute value graph looks basically just like the line y equals x. On the other side, when x's are negative, your output is always the opposite of x. So if I plug in -2, I get +2 back out. So I want to have the output be the opposite of x for all my x's that are less than 0. And so that's why this side of the graph looks like the line y equals -x. In the spring of 2015, Duke Energy Progress supplied electricity to residents in South Carolina for a monthly customer charge of $6.50 plus 9.997 cents per kilowatt hour for the first 800 kilowatt hours supplied in the month, and 8.997 cents per kilowatt hours for any usage over the 800 kilowatt hours in a month. So this is an application of a piecewise function. There's different things happening in different parts of the domain. For the first 800 hours, you get charged one amount, and then anything above that, you get charged a different amount. So different things are happening. So see if you can pause the video and figure out what the charge for using 300 kilowatt hours in a month is, and what the charge for using 1,500 kilowatt hours in a month is. So for the charge for 300 kilowatt hours, the person gets charged $6.50 just for the monthly charge, and then $0.09997 for times 300 kilowatt hours. So you have to be careful because the units are different, 9.997 cents versus dollars. So I converted this into dollars, and I got $36.49. For the charge for 1,500 kilowatt hours, this is where it gets tricky because for the first 800 kilowatt hours, it gets charged the first price, and then anything above that 800, it gets charged the second price. So I multiplied the 0.09997 by the 800, and then the 0.08997 by the 700, and then also included the $6.50 monthly charge, and you get $149.46. So now that we have that, see if you can use this idea to create a piecewise function that represents the cost C as a function of x kilowatt hours. So for the first part, it's pretty straightforward. There's the 650 plus the 0.09997x, where x is how many hours, and that's for 0 is less than or equal to x is less than or equal to 800. I made sure I included the 0 because you can't have negative kilowatt hours. The next part is a little bit trickier because we want to make sure we split off this 800 from anything above 800. So I calculated what this first part would be, the 650 plus the 800 first hours, and I got 86.476. So that's the cost for anything up to 800 hours. And then the additional on top of that is going to be 0.08997 times anything above 800. So for example, this was multiplied by 700, which was the 1500 kilowatt hours, minus the 800 we've already been charged for. You don't want to double charge for the stuff over 800. So you want to make sure you take out 800 and only charge for what's above it. And that's for all x's that are greater than 800. So go ahead and pause the video and see if you can try graphing this piecewise function. So here's the graph. It's a little bit hard to tell, but the nice thing about Desmos is it kind of separates the two pieces. So I only graphed it in the first quadrant, again, because you can't have negative kilowatt hours, so it doesn't make sense to go to the left of the y-axis. So this first part here is the first part of the graph, and then it very subtly adjusts its slope for the second part of the graph. So that's that breakpoint at x equals 800. So this has been parent functions and piecewise functions.